All right, welcome everybody. This is section 4.1. It's called Sample Spaces and Probability. Probability, if you read the paragraph right here, it says it's the define the chance of something occurring. You know, what's the chance of something happening, occurring? Here's an example. If there's a 75% chance of snow, you might hear the weatherman say that, maybe not in San Antonio. But if there's a 75% chance of rain, then there's a 25% chance of no snow, right? If 75% chance of snow, then that means there's 25% chance that there's no snow. And a probability experiment is a process um, with well-defined outcomes, and we're going to talk about outcomes today. An outcome is a result from a single trial. An outcome is a result from a single trial from an experiment. We say experiment, but it's just a way we say a group. We say it's an experiment. So an outcome is a result, something that could happen from a single trial. And here are some sample spaces of outcomes. So this is just another way of saying things that could happen, outcome. If you toss a coin, what could you get? What are some of the outcomes when you toss a coin? Anybody know? I'm using these set brackets.
Heads or tails?
Yeah, you could just get a head or a tail. Those are outcomes. Okay, so yeah, those are outcomes. You can get a head or a tail. When you roll a dice, what are the possible outcomes? Those are supposed to be set brackets, if I could.
1 through 6?
Yeah, 1 is on a dice, 2, 3, the number 4, the number 5, and the number 6 are all on a dice. Now, everybody should know this. If you've never rolled a dice or never seen a die before, now you need to know. So on a true false test, you could either have a true or a false. These are the outcomes. Tossing 2 coins. Okay, so this is a little different. You could have if you have 2 coins, you could have 2 heads. You could have 2 tails. Maybe I should put it like this. You could have a head and a tail, or you could have a tail and a head. Do you see there are 4 outcomes for tossing 2 coins? Can anybody think of another one? Head, head, tail, tail, head, tail, tail, head. I think that's it, right? I mean, unless you can come up with another one that I didn't write down. But if you have 2 coins, these are the 4 possible outcomes, and there are no others. On a true-false test, you could get a true or you could put down false. That's it. So these are outcomes of an experiment or a trial or whatever we want to call it. We can call it an experiment or a trial. So find the sample space of rolling 2 dice. So once again, if I could draw a dice here, let's see if I could draw a dice. There we go. Something like this. Do you see a dice? If we look at all the sides, a dice has 6 sides. So if we have 2 of them, 2 dice, we want to list all the outcomes. Well, I could roll a 1 and a 1. I could roll a 1 and a 2, a 1 and a 3, a 1 and a 4, a 1 and a 5, and a 1 and a 6. There are no 7s on a dice. Do you see? This is the first one dice, and this is the second one. Then I could roll a 2 and a 1, 2 and a 2, 2 and a 3, 2 and a 4, 2 and a 5, and 2 and a 6. Then I could roll a 3 and a 1, 3 and a 2, 3 and a 3, 3 and a 4, 3 and a 5, and 3 and a 6, 4 and a 1. By the way, I would write all these down because you're going to be using them over and over, and it's good to have them in front of you. This is a good thing to put on a formula sheet. All the outcomes for rolling 2 dice. 4 and a 1, 4 and a 2, 4 and a 3, 4 and a 4, 4 and a 5, 4 and a 6. This is why I told you this section is going to be long. 5 and a 2, 5 and a 3, 5 and a 4, 5 and a 5, 5 and a 6, and finally 6 and a 1, 6 and a 2, 6 and a 3, 6 and a 4, 6 and a 5, and 6 and a 6. So these are all the outcomes, I think, unless somebody could tell me one I didn't write down. I think I wrote them all down. How many total outcomes are there when you roll 2 dice? Anybody know? There are 36 outcomes. There are 6 here, 6 here, 6 here, 6 here, 6 here, and 6 here. 6 times 6 is 36. There are 36 outcomes when you roll 2 dice. Okay? Another way of looking at this, there are 6 outcomes here, and there are 6 outcomes here. If you have 2 dice, you multiply them together, and there are 36 total outcomes. And we're actually going to be using this method of finding the total number of outcomes later on. Stop me if anybody has any questions, because we're going to use these outcomes. Unfortunately, I have to erase them. Unless they're written down already, and I should really go scan down before I write these things down. Oh, they didn't have them. Here's the sample space for a deck of cards. Now, everybody, I found out that not everybody uses a deck of cards and understands what a deck of cards is, but this is a deck of cards. There are 4 suits. These are suits. Let's talk about that. They're called suits. Hearts, diamonds. These are called spades. Hearts, diamonds, spades, and clubs. If I could spell it. Clubs. That's a C. So there are 4 suits in. How many cards are there in each suit? Does anybody know? How many cards in each suit? How many hearts are there?
13.
Yeah, there are 13 in each. 13, 13. Anybody know how many cards there are altogether? 13 times 4 is 52 cards. So there are 52 cards altogether. 13, if you count them all there are 52 cards. Now, in the book and in the homework, they're going to say face cards. These are all face cards. Jacks, queens, and kings. Because when you look at a card, a jack, it has a picture of a man on it, a joker. If I could draw it. It has a picture of a man on it, which has a face. A queen has a picture of a woman on it, a queen. And a king has a picture of a man on it. So all 3 of these jacks, queens, and kings are face cards because it's a jack, joker, queen, or a king, and they all have faces, actual face. So we call those face cards. There are 3 times 4. There are 12 face cards in a deck. 12 face cards in a deck, so we need to know that. 13 hearts, 13 diamonds, 13 clubs. How many red cards are there? How many red cards are there?
26.
26 red, 13 and 13, and there are 26 black cards. 26 and 26 is 52. So we need to know this. Hopefully you guys are not sleeping, because I think this test is going to be a little trickier than the last test. All right, let's see what else. Let's scroll down. I think that's everything about cards that we're going to be using here. We're going to do the sample space for 3 kids. A, a husband and wife have 3 kids. Find the sample space for gender of children if the family has 3 kids. So we're going to have 3 kids. Child number 1, child number 2, and child number 3. We're going to have 3 kids. And I'm going to use something called a tree diagram. It's like a family tree, a tree diagram here. So when the woman has their first child, what are the outcomes for the first child? What could they have for the first child?
A boy or a girl?
Yes, a boy or a girl. This person could have a boy or a girl. On the second child, what could they have?
Twins?
Yes. No, but we're counting at 1 child each, but they could have a boy or a girl also, correct? And the third time, they could have a boy or a girl. So I just wanted to show you the first baby. We could call this the first child. Could be a boy or a girl. The second child could be a boy or a girl. The third child could be a boy or a girl. This is the third child. Okay, so if the first child, so I'm going to erase this for a second. Sorry, not that. If the first child is a boy, what could the second child be? I'm going to put here first child this way also. So let's just say I had a boy on the first child. What could the second child be? I'm running out of room. Let me see if I can scroll this up a little bit. I'm going to do it like this. Family. Sorry. So they could have a boy or a girl. I'm just going to do it like this. First child. If you have a boy, then the second child could be a boy or a girl. If the first child is a boy, then the second child could be a boy or a girl. If they had the third child, let's say they had a boy for the first child, a boy for the second child, then the third child has the ability to be a boy or a girl. If they had a boy, but then they had a girl, the third child could be a boy or a girl. By the way, I would write this little tree down that I'm doing. I'm going to move this G over a little bit so I give myself a little extra room. You could have a boy or a girl for the first child. The second child, if you had a girl, the second child could be a boy or a girl. And then if you had a girl and a boy, the third child could be a boy or a girl. If you had a girl and a girl, the third child could be a boy or a girl. So this is called the tree method, and we're going to list the sample space. We're going to list all the outcomes. And I'm going to use a different color pen. I'm going to use red. Do you see? I can use this tree to do all the outcomes. I could have a boy, and a boy. Do you see? First child boy, second child boy, third child boy. So my outcome could be boy, boy, boy. I could also have a boy, or maybe I should erase that. I could also have a boy, and then I could have a girl. Do you see boy, boy, and I'm sorry, my pen doesn't always work, girl. So I could have a boy, boy, girl. I use both of these up, so now I'm going to do this side. Boy, girl, boy. Boy, girl, boy. I could have boy, girl, girl. Boy, girl, girl. And that's pretty much it for boys being the first. Do you see there's no other path of the tree that I can take for boys being the first? I could have a girl first. Girl, boy, boy, girl, boy, boy. I could have a girl, boy, girl, girl, boy, girl. That's supposed to be a boy. I could have a girl, girl, boy, girl, girl, boy, and I can have a girl, girl, girl. If you look, each child has two outcomes, a boy or a girl. 2 times 2 times 2 is 8 outcomes. If I multiply those together, 8 outcomes. If you look, I have 8 outcomes here. And so we need to write those 8 outcomes down. Having 3 children, you'll probably have problems on the homework, on the test, that's going to be using these outcomes here. You could have tried to write them all down on yourself, but just hopefully you wouldn't miss one or anything like that. Forget to write one, because it's kind of important. All right, so those are all the outcomes. I'm going to erase this now. I'll give you a second if anybody's writing these outcomes. Once again, it's really important, I think, to take notes. All righty, let me erase. And let's move down. An event consists of a set of outcomes or probability experiment. An event is one or more outcome. It's called a simple event. If you just have with one outcome, it's called simple. I think that's actually a homework question. One outcome or more, or an event with one outcome is called a simple event. So just mark that if you have your workbook. So if a dice is rolled and it shows a 6, that's one outcome. That's a simple event. You just see the 6. Compound events consist of 2 or more outcomes or simple events, 2 or more outcomes. So a compound is just more than one. Let's see what else we need on here. We saw the quiz that we took, and we want to just, I'm not a big definition person, but they're on the quiz. Classical probability uses sample space to determine the numerical probability the event will happen. Classical probability, so we want this formula, the probability of an event happening equals the number of desired outcome divided by the total number. So that's what that says. The number of desired, the ones desired means is what we're looking for, divided by the total number of possible outcomes. And we're actually going to be doing that today. Probability of event, desired outcomes divided by the total number of outcomes. Mm-hmm. 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 All events should be equally likely. That means there's no cheating going on. Equally likely, that means if I roll a dice, I have the same chance of rolling a 2 as I do a 5. That means the dice are not loaded. Loaded means like you have something in them to roll a certain way. So each outcome is equally likely. It has the same probability of getting an answer. Now, rounding rule, we need to look at that. Probability should express as a reduced fraction. So reduce a fraction or round it to 2 or 3 decimal places. And they normally tell you what to round it to. When a probability is extremely small, you can round it to more decimal places than 2 or 3. But that's just every now and then you'll see that. And we'll actually have a couple of answers like that. They usually tell you what to round it to, how many decimal places to round an answer to. Okay, so find the probability of getting a red face card, Jack, Queen, or King, when randomly drawing a card from a deck of cards. So I want to put this is the probability of event happening equals the desired outcome divided by the total number of outcomes. Find the probability of getting a red face card when randomly drawing a card. So we have a deck of cards. We have a deck of cards. How many cards do I have to choose from? If I say I have a deck of cards, how many cards do I have to choose from?
6. Red face cards.
No, I'm just talking about a deck of cards.
52.
52. Do you see? That's the total possibility of me picking. That's my total out. If it says I'm picking one card from a deck, the total is 52. There are 52 cards I can choose from. But somebody said face card, red face card. There are 6. Then they said 6 because we have hearts and we have diamonds that are both red. So there's a Jack of Hearts, a Queen of Hearts, and a King of Hearts, a Jack of Diamonds, a Queen of Diamonds, and a King of Diamonds. So there are 6 face cards, red, out of 52. 6 out of 52. So our answer has to be a fraction, and it has to be a reduced fraction. Anybody know what the answer should be? So let me show you this on the calculator, just because, just in case you can't. By the way, you normally would reduce fractions. They both divide by 2. So this is the actual answer. But I'm going to show you how to reduce fractions on our calculator. So I'm going to show how to reduce fractions on our calculator. So we said, where's my focus? There we go. We said the answer was 6 divided by 52. So, and my calculator gives me a decimal, but if I hit the math button, and number 1, it changes all decimals to fractions. You just hit enter, and it reduces it to 3/26. So 6 divided by 52 equals this. If I want to know the fraction answer, I go to math and number 1 fraction, hit enter and hit enter again, and it reduces the fraction. It divides the top and bottom by whatever it has to. In this case, it's 2, and I get 3/50 or 3/26. So your calculator will reduce fractions for us. So when we did it ourselves, let me come back here. We got 6/52, put it in our calculator, and we ended up with 3/26. What we did was your calculator divided the top and bottom by you have to divide the top and bottom by the same number, and we get 3/26 as our answer. The probability of getting a red face card is 3/26. If a family has 3 children, find the probability that exactly 2 of the children are girls. Remember, our 3 children were boy, boy, boy. I can't remember, boy, girl, boy, 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 girl, and I've got to write them all down again because I erased them. Boy, 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 girl, girl. Oh Lord. Then we had girl, 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 boy, boy, girl, boy, girl, 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 boy. I think these are it. Wait, girl, girl. I think these are all 8. Remember, there were 8 probabilities. Find the probability exactly 2 of the 3 children are girls. Probability of the event that exactly 2, that I'm going to just put at exactly 2. The probability that exactly 2 are girls equals the desired outcome. Desired outcome is how many are girls, or exactly 2 girls over the total. Anybody know what the total is supposed to be in this problem? What should the total be?
8.
8. There are 8 outcomes that we wrote down for 3 kids. There are 8 possible outcomes. And the desired of 2 girls. So it said exactly 2 girls. Here are 2 girls. Here are 2 girls. Wait, no, that's 3 girls. Sorry, that's girl, girl, girl. Here are 2 girls, and here are 2 girls. So 3 out of 8 are 2 girls. 3/8. The probability, if you had 3 children, the probability of having exactly 2 girls is 3 out of 8. There are 8 outcomes possible. Only 3 give you exactly 2 girls. Once again, desired is what we're looking for. We're looking for exactly 2 girls. We're looking for exactly 2 girls. That's what's desired. And 3 of them have exactly 2 girls. All right, let's move on down. So there's a couple words that we're going to look at, and we'll look at them more in detail, I think, in the next section. The word and or. And means the event has to happen at the same time. A and B. That means A and B have to and the word and is it has to happen at the same time. I'm going to use another word for and that I want you to write down, the intersection. When two cars come together at an intersection, they come together at the same time. An intersection. So and means intersection at the same time. Now, or the word or depends on what kind we're talking about. Normally, or means a union, and I'm going to use we use the intersection for and, or I'm going to use union. Or is a union, and another word for union is marriage, right? We bring these two together to form a union, to form a marriage. Inclusive and exclusive. I'm not going to write anything down for those yet. Hopefully, I think there might be something coming up. I don't want to write anything down because we have two separate formulas for that, inclusive and exclusive. That means if they affect each other or they don't affect each other. And that's why I don't want to write anything down for those. We might come back and write something down later, but we'll look at the formula coming up here in a little bit. Let's see what we have here. Okay, a card is drawn from an ordinary deck. Once again, the probability of an event happening is the desired outcome. And it's the number of desired outcomes divided by the total number. That pound symbol means number. Find the probability of A of getting a king. So we know there are 52 cards in this deck. How many kings are there? Probability of getting a king. How many kings are there in a deck?
4.
Yeah, there are 4. So what would this answer be? It's 4 over, if you type in 4 over 15, it's wrong. Or you look on multiple choice, so there's no 4 over 15. What's 4 over 52? What's the correct answer? Anybody got their calculator handy to see how this reduces?
2 over 26.
It reduces even more than that. You didn't use your calculator.
1 over 13.
I type in 4 divided by 52, hit math, and you get 1 over 13. Math fraction, and you get 1 over 13. By the way, you got 2 over 26. If you notice 2 and 26 are both even, you can divide by 2 again, and you get 1 over 13. So the correct answer for this, A, is 1 over 13. B, 4 spades. What's the probability of getting 4 spades? A card is drawn. A card is drawn from an ordinary deck. Find the probability, of getting the 4 of spades, not 4 spades. The 4 of spades. There are 52 cards in a deck. How many 4 of spades are there?
1.
Yeah, there's only 1 4 of spades. There's 1 4 of spades, 1 4 of hearts, 1 4 of diamonds, 1 4 of clubs. So 1 over 52, it reduces to 1 over 52, doesn't reduce. So that's the answer to B. C, once again, there are 52 cards altogether. A face card We looked at it, and there's 4 jacks, 4 queens, 4 kings. So when we looked at the deck of cards, we knew there were 12 face cards. On my calculator, 12 divided by 52. I would really practice this now. Go to math, number 1, and it reduces to 3 over 13.
Is it 1/5?
Say that again?
Is it 1/5?
It's 3 over 13. You 12 over 52, you should get 3 over 13. That's a 52. 12 divided by 52. You should get 3 over 13. A red card, there are 26 red cards, by the way. So when you reduce that, you get 1/2, 26 over 52. Half the cards are red, half the cards are black. And E is a club. There are 13 clubs and 13 diamonds, 13 spades, and 13 hearts. So 13 clubs, and that reduces to 1/4 when you put that in your calculator. So make sure you're able to reduce these fractions correctly on your calculator. Now, if you don't reduce the fractions and type it into the homework, I think it's going to mark it correct. They might say, hey, reduce the fraction. But on the test, if you end up with 13 over 52, you won't see a multiple choice answer for that. So you're going to have to be able to reduce it on your own. Okay. Any questions on these?
No.
Okay. Speaking for everybody. All right. All righty, let's see where we're at now. Is it moving? What happened? Oh, there we go. All right, so now we have some more questions to go over. These are like homework problems. If you notice here, it says if a dice is rolled 1 time, find the probabilities of getting an odd number. So if a dice is rolled, remember the outcomes for a dice are 1, 2, 3, 4, 5. The probability of an odd number, remember desired on top, total on the bottom. What's the total outcomes on the bottom of rolling a dice? There are 6 ways for me to roll a dice and get, there's 6. The total is 6. Now it says the probability of getting an odd number. How many odd numbers are up here?
3.
Yeah, 1 is odd, 3 and 5. So that reduces to 1/2. The probability of getting an odd number is 1/2. The probability of getting an even number is 1/2. When you roll a dice, the probability of getting an odd number is 1 out of 2. 1/2. All righty. Okay, so once again, the outcomes on a dice were 1, 2, 3, 4, 5, and 6. Getting a number greater or equal to 3. Greater or equal to 3. First of all, there are 6 numbers altogether. Probability of getting a number greater than or equal to 3. How many numbers are greater than or equal to 3?
3.
Not 3. Let's underline them. 6 is greater than or equal to 3. 5 is greater than or equal to 3. 4 is greater than or equal to 3. Is 3 greater than or equal to 3?
Yes.
Yes, greater than or equal, one or the other. It's or equal. So there are 4 numbers greater than 3 or equal to 3. And when this reduces, the answer is 2/3. Okay, so the next problem, probability that is greater, it doesn't say equal to, it says greater than 3 and even. Remember, and means that it has to happen at the same time. There are 6 numbers total. How many numbers are greater than 3 and even? How many numbers are greater than 3 and even? Anybody? Greater than 3 and even. Do you see 4 is an even number and is greater than 3? 6 is an even number than greater than 3. There are 2 numbers, greater than and even. Greater than 3 and even. It reduces to 1/3. Please, I hope everybody's paying attention. I know some of you guys are watching Oprah or whatever's on right now. Is Ellen on right now?
No.
Who's Ellen got on right now?
I
What are
don't
you
know.
guys watching? Netflix? I know it. I'm telling you, at the end of the semester, people always say, what can I do to pass this class? You could have paid attention during the lectures. It's too late then. Moving on. Okay, here we go. Here are 3 questions. A set of 25 2-digit numbers. So if we count all these numbers up there, there are 25 numbers written down there. Choose one of these numbers at random. Find the probability of the results. So we know there are 25 numbers total. Do you see there are 25 outcomes up above us? That's the bottom. The total is the bottom. Now the top is desired. Desired is how many of those numbers are even, the number of even numbers. Even numbers end in an even number at the end. Do you see that's even? Even. 19 is not even. That's an odd number. That's even. Even. 36, 40, 44, 46, 52. 55 is not even. Even, even, even. We're looking at the last digit to the right to determine if they're even or odd. These are all even numbers. There are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 out of 25 that are even. And that reduces, when you put that in your calculator, to 3/5. So out of all those outcomes up there, how many are even? 15. 15 out of the 25 reduces to 3/5. Okay, that was part 1. Hopefully I did it right. As far as I did all the even numbers and all. Let's look at part 2 now. Part 2, by the way, you're going to have a homework problem like this. I mean, it's really be beneficial to watch this and then do the homework right afterwards. It says the sum of the numbers digits is even. So when you add them up, is it even? The sum means even. So I'm going to take the sum of these numbers. Look, 1 and sum of the digits. 1 plus 0 is 1. 1 plus 6 is 7. Do you see 1 and 9 is 10. 2 plus 1 is 3. 2 plus 5 is 7. 3 plus 0 is 3. 3 plus 5, 8, 9, 4, 8, 10, 7, 10. 5 plus 6 is 11. 6 and 2 is 8, 11, 13, 9. I don't know what that is, 12. 13, 8. 8 plus 0 is 8, 13, 16. 9 plus 7 is 16. This is 17. So it says the sum of the numbers digits. Digits are each individual digit part. And so it says, so we know we have 25 numbers up there. We know we have 25. That's the total. Now we have to find the even numbers when we added them. When the sums are done, how many even numbers do we have? And I'm going to circle them in red. 10 is even. Do you see? The sums are even. 8 is even. 4, 8, 10, 10. 8 is even down here. 9, no. 12 is even. 8 is even. 16 is even. 16 is even. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 out of 25 are even when you add up their digits and find their sum. Okay, and that does not reduce. When I put 11 over 25, hit enter, and then go to math number 1, it still says 11 over 25. All right, let's erase these and do the last one now. It says, out of these 25 numbers, how many are greater than 50? Luckily, they're in order. All of these are greater than 50. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 are greater than 50. I don't think it reduces, so we are done. 14 out of 25 are greater than 50. Stop me if anybody has any questions. It's kind of important. Want to make sure everybody's on the same page. Don't forget, you can use all the notes you want on the test. The next test is going to be a little harder, I think. But if you take notes, do the homework, and stay current in the class, it won't be too bad. All right, a little bit about probability. Probability of an event, it could be a fraction or it could be a decimal. All probabilities are between 0 and 1. By the way, this is homework problem, and this is also a test question. All probabilities are between 0 and 1. You always hear the basketball players saying, or football players, I gave it 110%. No, you can't give it more than 100%. You can't. 100% is everything. So your all probabilities are between 0 and 100%, or 0 and 1 fractions or decimals. Do you see 0.5 is 50%, 50-50 chance? A probability of 1, we know it's going to happen. That's 100%. A probability of 0 means it's impossible. It's not going to happen. If you have a probability that equals 0, it is not. You have a 0% chance of rain. It's not going to happen. But the weathermen are really terrible. Usually when they say you have a 100% chance of rain, you look out the window, it's already raining. Yeah, we know that. There's a big storm. All right. So all probabilities have to be between 0 and 1. out of this, by the way, this is a homework question that we're looking at right now. This is a homework question. It said, a probability is conducted. Which of these cannot be a probability? Negatives are not allowed to be a probability. So this is the answer. Negatives cannot be a probability. So you can't have, I have a negative 27% chance of winning. There's no such thing as a negative. Between 0 and 1, that's good. Fraction between 0 and 1, that's good. 23%, change it to a decimal, is 0.23. That's okay. 105%, no, you can't have 1, the decimal 1, when you multiply it by 100, change it to a percent, is 100%. You can't have, the probability has to be between 0 and 1, 0 and 100%. It can't be more. So you can't be negative, and it can't be more than 100. Zero's okay. It cannot be negative, and it cannot be more than 1. So all of these are bad answers. It says which ones cannot be probabilities. Negatives cannot be probabilities. You cannot have more than 100% or more than 1 when you're looking at the digits or decimal places. Percentages, you can't have more than 100%, and you can't have negatives. So the ones I circle are the ones you cannot have as a probability. It's on the homework, and I'm sure this is a test question. Cool. When you have all the outcomes, well, let's say you're rolling a dice. Can somebody tell me, if I roll a dice, here's a dice. When I roll a dice, what's the probability of getting a 6 on the dice?
1/6.
Yeah, there are 6 total numbers on a dice, and there's only 1 6. The probability of getting a 6 is 1/6. Probability of getting a 5, there's only 1 out of 6, so that's a 5. There's only 1 4, 1 3, 1 2, 1 1. Now, if you add these up, 1 6 plus 1 6 plus 1 6 plus 1 6, probabilities have to add up to 1. When you add up all the outcome probabilities, it has to equal 1 or 100%. You see, you have to include everything. So it has to add up to 1. That is really important. The probabilities, all the outcomes have to add up to the number 1 or 100% if you're doing percentages. If an event cannot occur, then it has 0 probability. If there's 0 chance of rain, it cannot occur. Okay, here's a good one. When I roll a dice, here's my dice. What's the probability of me getting a 9?
0.
There are 6 outcomes on a dice. None of them are 9s. So 0 divided by 6 on my calculator is 0. It's not going to happen. If you don't have a 9 on your dice, you're not going to roll it. There are 0. Desired is a 9, but on my dice, there's no 9s. I only have 1 through 6. 0 out of 6. 0 divided by 6 on my calculator is 0. The probability of getting a 9 when you roll a dice is 0. Now, rolling 2 dice is different when you add them up. But rolling 1 dice, the probability of getting a 9 is 0. Once again, if you're absolutely certain it's going to happen, the probability equals 1. What's the probability, when rolling a single dice, what's the probability of getting a number less than 7? There are 6 numbers on a dice. Probability of getting a number less than 7. Well, all the numbers on a dice are less than 7. 6 out of 6. The probability is 1. When rolling a single dice, what is the probability of getting a number less than 7? It's 100%, 1, because all the numbers are less than 7. It doesn't matter which number you pick, you're going to get a number less than 7. Desired outcomes, each one of these is okay because they're less than 7. Okay, let's write this down here, but let's put a star by this. The complement of an event. The probability of an event equals, let's say, 0.75. Then you're going to see something like this. The probability of event with a line on top of it. This means not the event. And it's also called the complement. We also call that line the not line. The probability of not. If, let's say, it's the probability chance of rain is 75%, then the probability of not is 0.25, 25%, because they have to add up. The event and not the event have to add up to 1. 0.75 and 0.25 add up to 1. So the complement is the opposite of the event. We put the line on top of it, and we call that line the not. This is the probability of rain is 75%. This right here, we say the probability it's not going to rain. That line means not. It's not going to rain is 25%. If rain is 75%, then not rain is 25%. So you start getting used to saying that line on top as not an event or not going to rain. All righty. Find the complement of each event. Rolling a dice and getting a 4. Well, getting a 4 on a dice, the probability equals 1 out of 6. What's its complement to 1 out of 6? Anybody know? The probability of getting a 4, I should have wrote it like this. Probability of getting a 4 is 1 out of 6. What's the probability of not getting a 4? Well, getting a 4, there's only one 4. Not getting a 4, there's 5 numbers that are not a 6. I mean, there's 5 numbers that are not a 4. You get a 1, 2, 3, 5, or a 6. So the complement of 1 out of 6 is 5 out of 6, because 1 out of 6 plus 5 out of 6 equals 6 out of 6, which equals 1. Remember, when you add up the complement and its event, it has to add up to 1. Selecting a letter in the alphabet and getting a vowel. The probability of getting a vowel in the alphabet. Uh-oh, this is a tough one. How many letters are there in the alphabet? English. Anybody got it? Remember?
26.
There are 26 letters. How many vowels are there? A, I, O, U.
A-E-I-O-U.
A-E-I-O-U. There we go. 5. So there are 5 vowels. It's the probability of a vowel. So the probability that you're not a vowel, the complement, is 21 over 26. Do you see 5 out of 26 are vowels? That means 21 are not vowels. Probability of not being a vowel is 21 over 26. Anybody know, we have vowels. What are the other letters called that are not vowels? They have a word to them. I don't remember.
Consonants?
Consonants?
Yes, consonants.
Okay. I thought they had another word to it, but we'll use that. Consonant. Let's try the next one. selecting a month and getting a January. So probability of a J in the month. Well, we know there are 12 months in a year. Getting a month that begins with J, January, June, July. I think that's it, right? With J, January, June, July. 3 of the months have J in them, begin with J, which reduces, by the way, to 1 out of 4. So the probability that they don't have a J at the very beginning would be 3 out of 12. There's 9 left. 9 out of 12. Do you see 3 and 9 add up to 12? And that changes to 3 out of 4, reduces to 3 out of 4. So if the probability is 1/4, its complement is 3 out of 4. 1 out of 4, its complement is 3 out of 4. 1 out of 4 plus 3 out of 4 equal 1. Selecting the day and getting a weekday. Well, there are 7 days in a week. 5 of them are weekdays, and its complement are the weekends, Saturday and Sunday. Probability that they're a weekday, probability that they're not a weekday is 2 out of 7. So its complement is the opposite, or they have to add up to 1 when you look at these two. 5/7 plus 2/7 have to add up to 7/7, which equals 1. I'm not going to look at this yet. We have these formulas here. You could write them down and use them. The probability, anybody, what does this, once again, that means the probability that the event will not happen. The probability that the event will not happen is 1 minus the probability that it will happen. It will happen. You see, probability event will happen is 1 minus the probability that it will not happen. If you add up the event and its complement, they always add up to 1. So we need to remember that they have to add up to 1. So let's look at this problem. In a study, it was shown that 23% of people surveyed said vanilla was their favorite. So the probability that vanilla is your favorite is 23%. That's what it says. Vanilla is 23% is your favorite. If a person is selected at random, find the probability that their favorite flavor is not vanilla. Find the probability that your favorite flavor is not vanilla. Anybody know the answer? If the if the probability that you're getting your vanilla is your favorite is 23%, what's the probability that vanilla is not your favorite?
23/77?
No, it's just 77%.
Okay.
You see, they have to add up to 100% or 1. 23 plus 77 equals 100. Another way of doing this, if we go up to the top, I just want to go up to the top once again to that formula. Probability of it not happening is 1 minus the probability that it is happening. So the probability, if I look at the probability on my calculator or here, the probability that event not happening, that vanilla is not my favorite, is 1 minus the probability that it is my favorite. Vanilla is my favorite. This means not. If this is 1 minus 23%, we can change 23% to decimal, which is 1 minus 0.23. On my calculator, that will be 0.77. Change it back to percentage at 77%. So if vanilla, 23% is vanilla is their favorite, then the people that not vanilla, it could be any other flavor, is 77. They have to add up to 100%. If you change it to decimal form, it has to add up to 1. Okay. If the probability that it will rain, the probability that it will rain is 0.2. What's the probability that it won't rain? Somebody's typing it in. Let me get 0.8. Thank you, Chastity. Once again, it's 1 minus the 0.2, which is 0.8. 0.8. These two have to add up to 1. Let's move on. So empirical probability relies on actual experience to determine the likelihood of an outcome. Once again, it's the sum of all frequencies divided by the desired. It's the same formula, desired divided by the total. Total means to sum it up, add it all up. So probability of an event happening is the desired divided by the total. So if we come down here, suppose for an example, researcher of American Automobile Association asked 50 people. Do you see when you add these three up, there are 50 people total. Total is 50. I don't even know what the question is, and I'm already filling in the problem. Total is 50. For example, who plan on traveling over Thanksgiving, how will they get to the destination? So here's a table that talks about their destination. Let's see what the questions are now. Was there, oh, is there any question?
I think you were I think you passed them. You're going to them, sir.
Oh, okay.
I think. I don't know, maybe I'm wrong.
No, this is blood types. This is different. Okay, so I'm going to make up a question. What's the probability that what's the probability that somebody flies? The total was 50 possible people. Only 6 flew. 6 out of 50, which reduces to 3 out of 25. So, I mean, the only difference here is that you have to, just add up the total frequency. How many of each? They asked people, 6 people said they fly, 41 people said they drive, 3 said they took the train or bus. 50 people total, so 6 out of 50 flew. All right, here's blood types. Are we near the end? Boy, there are a ton of, oh my. Okay, that is the end. So we got a little bit more to go. I told you this was a long section. It's really important. Okay, so we have 50 people. So that's telling us that the total is 50. That's the total. There are 50 people here. 21 had O. I'm going to write it down. 21 had type O. 22 had type A. 5 had type B. and 2 had type AB. That doesn't mean they had A and B. It's AB. They're just different types. If you add those up, it adds up to 50 people, okay? Set up the frequency distribution and find the probabilities. Find the probability that somebody has type O blood. Probability type O. Well, there are 50 people total, and only 21 have type O. That's it. It doesn't reduce. That's the answer. Part B, a person has type A, probability of type A, or type B. Okay, so here's the word or. Or means union. It's like a marriage, an intersection, or and is the intersection, or is a union. That means we're bringing it together. How many A's are there?
$22.
And how many B's are there?
5.
So, or we're adding them. It's a union. We're adding the stuff together. So 22 plus 5 is 27 out of 50. Have type A or type B. 27. Oh, by the way, I don't think that reduces. No, that doesn't reduce. They don't divide by 3 or 9. Yeah. So that doesn't reduce if you try to reduce that in your calculator. You always try to reduce the fractions. So part B is 27 out of 50. Okay, the next one's a little tricky, maybe. Probability, this is question C. A person has neither type A nor type O. That's hard to write down. Neither A, that means they don't have A or they don't have O. So let's look at all the ones that don't have A or don't have O. B is not A or O, and 2, AB is not A or O. So we can't count these because it says neither A nor O. So the answer is 5 and 2, 5 plus 2 over 50, which is 7 out of 50. And finally, let's do D. D is a person does not have type AB. Probability that you don't have type AB. Here's AB. Only 2 people had AB. That means 48 don't have type AB. Do you see? If 2 have AB, then 48 don't have it. 48 out of 50, which reduces to 24 over 25. So those are tough. I mean, you can see you really have to practice these to understand what they're trying to tell you. And the best way to do that is to write them all out in some kind of a table form, the frequency table like we had above. Or even just write them down like I did. They're easier to visualize. Okay, so here it says elementary and secondary schools were classified with these number of computers. Choose one school at random. Find the probability of the following. Enter your answers in fraction or decimals to 3 decimal places. Probability of 50 or fewer computers. So first of all, 50 or fewer, how many go, the number goes on top, that's desired. How many choose a school, how many schools were there total? How many schools were there total? Right, that's the bottom. To find the total schools, you have to add all of these up. These are all the schools. This is the frequency. We have to add them all up on our calculator. 4388 plus 4866 plus 17, 573 plus 25, 043 plus 35, 264. So when I added them all up, I got 87,134. I hope that's right. I'm hoping somebody checks my work. 87,134. So how many were 50 or fewer? Do you see this is 50 or fewer? These three are 50 or fewer. So we're going to just add these three up. 50 or fewer computers. So 43388 plus 4866 plus 17573. And when I added those up, I got 65,827. And I'm going to put that in my calculator, divided by 87,134. It says round to 3 decimal places. I get 0.7554. If it says round to 3 decimal places, I take it to 4 decimal places. 4 or less, you don't change the number. If that 4 was a 7, then it'd be 0.756. You'd add 1 to your last decimal place. But since it's a 4 or less, you don't change anything. And the answer to this would be 0.755. Everybody okay with this problem? The total, you have to add up all the frequencies, all those schools up, 87,135. And then the top is desired. Which one had less than 50 or less computers? You had to add those 3 categories up and then put it in your calculator and get the answer. I'm not going to do any more of those. I think that should be fine. Subjective probability uses probability valued based on educational guess. So subjective is kind of like guessing. It's an educated guess. So make sure we remember that. Weather forecasting is in it. We're guessing that a week from now, you're going to have a 10% chance of rain. How do they know? You know, next Monday, you have a 10% chance of rain. Normally, they know about a week in advance because they see these storm systems coming, but they could fall apart and it could not rain. I mean, they're predicting future. It's a guess. With looking at all the information given to them, it's an educated guess. And I think that's all I wanted to give you today. If you look at the rest of these, these are homeworks. You could take a look at some of these. Once again, getting a royal flush. Is it empirical, classical, subjective? I want you to go back and take a look at it and see what the difference between all 3 of those are. I would write them all down and put an example of each down. Once again, when we look at classical probability, when we look at above right up here, I'm sorry, it's hard for me to move throughout the screen. It won't let me. When we look at subjective probability, it's an educated guess. So, you know, when the probability of getting a royal flush is definitely not a guess. That's definitely a hard number. There's no guessing there. You can get one royal flush out of 649,000 different hands. So they don't tell you how to do that, but they want you to understand that's not subjective. Is it classical or empirical? And I want you to look at those and write down what each is and an example of each. that's all I had for the day. Let me hit stop recording.